would like to kickstart this event of RoboWeek 2021.
Universe is like a soup of consciousness. Brain is just a receiver. Simulating the behavior of 100 billion neurons of human brain is not feasible by classical computers, but quantum machine learning promises to fulfill that requirement. With this, a very warm good evening to everyone. I'm Vanshika Gyanchandani.
And I, Spurgeon, on behalf of Robotics Society and IDM Mirpur, welcomes you all to this enthralling talk on quantum machine learning. As you all are well aware, the technology is growing exponentially day by day. Quantum computing and machine learning are two such buzzwords in the field of computer science which are playing a vital role in the same. But ever wondered, what if we combine our knowledge of the quantum world with the modern machine learning and artificial intelligence? What impact can it have on our technologies?
Will it be useful for mankind or we are just slinging arrows in the dark? So to solve all your queries, we are pleased to have Dr. Santosh Kumar Nanda sir with us. He is a Vice President of Artificial Intelligence and Data Science Services at Techversant. He is an eminent data scientist and AI researcher, strategist and thought leader, having more than 15 years of industry experience.
Sir is a technical expert and corporate leader, recognized for delivering scalable and distributed software systems, resolving complex, mission critical challenges, and managing varied stakeholders. He has published two books and 50 plus quality research articles and also filed two patents in the field of AI and ML.
Sir is an editor in AI, ML, Data Science Journals, keynote speaker, and IEEE senior member. In 2014, Sir has been selected as a member in World Federation of Soft Computing. That's a very great achievement in itself.
We have a lot more to say about the achievements of Sir. But for now, we request Sir to guide our enthusiastic audience on the topic of quantum machine learning and to motivate them to have a brighter future in this field. Please, Sir.
Okay. First of all, good evening to all of you. And my sincere thanks to uh, NIT Hamirpur Student Society who invite me for this talk. And yeah, I'm humble and I grateful to all of the students who are today present to listen this concept. Uh, okay, so start this concept. I have two presentation. I'm audible to all of you. Please let me know that if there is
So you
any.
are
Yeah, excellent. So I have two presentation for all of you. One is the like I know that most of the students is from in second year and third year students are there. It is a very brief concept. It's a very complex concept. I want to start with a simple concept to quantum concept, and then I have a hands-on session for all of you. I need to guide you all of you that how we can start the quantum machine learning projects, how it is there slowly one by one. Okay, let me share my screen now. Oh, okay, it's asking for to upload the files. Yeah. So is it visible to all of you? Is my screen is visible to all of you?
no for now.
Okay. What happened?
But it's
How it is right now? Is visible?
yes, sir. Now it's visible. Yes.
Yes, sir, it is.
Yeah, excellent. So let me start with this era of AI machine learning, how it starts, when it starts from AI is not a new concept. It starts from 1950. A lot of contribution has been made. I completed my PhD in AML. So long back, a lot of people are, involved in AI and machine learning, and a lot of improvement is there from 1950 onwards. Right now we are in deep learning. A lot of activities that has been made it. So the verticals of the business in AI is, there are a lot of verticals there, like healthcare, IoT, then sales, then insurance. A lot of solutions are there. And we pretty in good position in business in AI related. The software solutions right now very impactful to solve client requirement in terms of business. So AI is a very big field right now, and if all of you want to start a career in AI machine learning, it's a golden period, and I believe that next 15 years still demand will be there. So when we are discussing the part of the artificial intelligence, there are a lot of processes there. It's not only machine learning. There are machine learning is there, computer vision is there, natural language processing is there, image processing is there, digital signal processing is there, optimization, export systems. It's a combine of lot of branch of artificial intelligence. It's a set of all of this component, and without that you cannot solve a problem, the complex problem. See, if I talking about the machine learning part, there are many types of machine learning is there. Supervised machine learning, reinforcement, unsupervised learning is there. In supervised, there are a lot of models are there, like multi-layer perceptron, adaptive neural fuzzy information system, radial basis function, support vector machine, support regression, hybrid model is there. Then reinforcement learning, unsupervised learning is there, k-mean clustering, nearest neighbor, principal component analysis. There are a lot of uh, models are there that is directly or indirectly we are using in our day-to-day activity. See, these are the major industry requirement in AI machine learning. If you want someone want to start a career in machine learning or something kind of that, then a candidate should be have knowledge in these are the areas where the candidate should have knowledge, depth of knowledge. Otherwise, he cannot able to start a career in this ML and AI part. So the student who wants to be a part of a IT project in future after his 4 year graduation study, then the student should be have knowledge about natural language processing, computer vision, ensemble machine learning approaches, deep learning algorithms, reinforcement learning algorithms, supervised learning algorithms. So these are the things that the candidate need to be should be know about all the things like. So when you're talking about the AI and ML model in industry, look, the way we are solving the model, like now I'm talking about the classical machine learning activities, where we have some of data. So when you have a business problem, we need to understand what is the business is there, what is the business problem is there. So according to that business problem, we need to have a good understanding about the what type of data is there. So we need to have good understanding data analytics. Then we need to like when we start a AI machine learning project, the client always sharing the raw data with you. So you need to understand that what type of data it is, whether it is a speech, whether it is a image, whether it is a textual data. You need to understand as a data scientist or AI engineer. uh, when you're talking about the classical machine learning part, then we need to handle the data. We need to data filtering. We need to adapt a lot of data filtering mechanism. We need to remove the noise, remove the outlier from the data. Data need to be smooth. Data need to balance, so that we can develop a model for that. Then we need to develop a best model for this, and that model need to be validated. So we need to have a set of data for validation of the model, and then we need to deploy the model. So now the deployment, all of the models in industry, 95% client wants to deploy their model into cloud. So there are a lot of cloud architecture is there. Google Cloud, IBM Cloud is there. Then AWS, Amazon Web Service clouds are there. Then Microsoft Azure is there. So these are the platform where we deploy the model, and in terms of a RESTful API architecture. So this is the role of AI machine learning in industry point of view. So till now, what are the data we receiving? How the way of in terms of speech, in terms of uh, uh, video, in terms of text data, in terms of numerical data. What are the data is we're receiving? Big data like telecoms domain. There are a lot of big data is there. So to handle this type of data, you need to do some distributed computing. So till now, there are good mechanisms there, but suddenly you can see that there is a very huge improvement in data part. Actually, the way 5G already come to market, and you know that this is a high speed data processing protocol, and where you receive a huge number of data within a second. So this classical machine learning models that already available in the literature, maybe it is a TensorFlow or Kera or scikit-learn, whatever the model is available in Python domain, that is not suitable for to handle high speed data, or to handle high volume of data. So definitely we required a alternative method where we can proceed with high volume data within a second, so that we can deliver a faster solution to the end user. The end user means we need to download a movie within a second. We need to travel with the data within a second, like kind of things. So right now world is running in a faster way. So typically if you dependent on the classical machine learning, the way we cannot deploy, you can deploy the model, but that deployment will be slow, and it can handle with the data quality changes, the way it is receiving from high speed data you know uh, uh, models like the 5G kind of thing. So we need to change, we need to move to a alternative method. So that's why we need to understand what is a classical machine learning first. This is my, like, this way I designed the presentation like that. So see, what is traditional programming is meaning, and what is the machine learning is meaning, like. So how we do the statistical programming earlier? So we have data, okay, and we develop the code and the program, and we upload to the computer. And when a new data comes to the computer, the available code can understand the data and getting the output. That's the traditional programming. But in machine learning, we need to make a relationship between the data and the output, and the code make a program, make a model, so that when a data comes to the system can understand, oh, this is the output.
Yes, sir.
So yeah.
Sir, actually, there's some technical problem from my side. Your screen is not visible on the YouTube. Uh,
Okay,
so, actually, it has not been started yet on the YouTube.
then what we'll do?
Sir, give me just 2 to 3 minutes. Let me resolve the issue.
Okay, it's a technical issue, right?
Yes, sir.
Okay.
Hello. Hello, sir.
It is done.
Sir, yes, sir. There was some network issue. You can
Okay.
start where you are, sir.
Okay, great.
You
So
can resume now. Yes, sir. You can present
uh,
the screen, sir.
now it is visible to all of you.
Sir, it's on the way. Yes,
Coming.
sir. It is visible. Yeah.
So shall I
You can
start from
resume.
here or shall I start from beginning?
No, sir. No, sir. You can start from here.
Okay, great. So where here I okay. So sorry for the disturbance. Okay, fine. Thanks all of you to handle this issue. So when you're talking about the machine learning, that means we need to make a relationship between the data and the output, and make a program, and that program itself a function. I'll explain how the machine learning will be designing in that way, very in a very brief way. So this is the concept between the traditional programming and the machine learning. So what happened when you develop such kind of development, like when you develop a relationship between the data and the output, when you deploy to somewhere, so that is fixed, no need to rewrite the program or no need to change the program until and unless there will be some changes in the data. So if a similar type of data comes to the computer, the program itself, the function itself can understand the data and make a exact relationship between the data and the output, and you get the exact output. So that is the beauty of machine learning, and that's why it is right now everybody is looking for machine learning, activity. See, when you're moving to the data kind of things, because it's very important before moving to the quantum machine learning, so we need to understand what is discrete data and continuous data. Generally we have a lot of data to handle. So time series data is there. So we may have a continuous data, we may have a discrete data, or we may have a time series data. So this type of data is there in classical machine learning. That's why each kind of data you need to develop models. But in quantum machine learning, you may not depend upon the data, whether it may be a time series, whether it may be continuous, maybe discrete. The model can handle all of the things. That's the beauty of quantum machine learning. uh, when you're talking about the data, see, this is the example of data where you can see that in this table where uh, some of data related to ordinal data like ID, textual data like name, Ramesh, Mera, Gita, Jonal, Gopal, Paul, like this, the name are there. Date of birth, interval data. So then we have gender, like kind of male or female as binary data. Then credit rating like AA, BC kind of ordinal. Then country kind of India, Ireland, US, second categorical data. Then salary kind of thing. This is numerical data. So these are the data types. So here in classical machine learning also, you need to handle the data type. Even that is essential for quantum machine learning also. You need to define whether it is a floating parameter or is a numerical parameter or is a whether textual or is a ordinal kind of that. So that is required to understand when you started your machine learning activity. You need to have strong knowledge in data types. You need to understand which data I need to go with the model making. Like you cannot develop a model with ordinal data, you cannot develop a model with textual data, you cannot develop a model with interval data, you cannot develop a model binary data. So we need to convert to some of editable way. Like you need to convert, like if I want to develop a model with binary data, then I need to convert the binary data to the numerical data. I can convert male to 0, female to 1, then I can develop a model. So let's discuss about the way the demand of machine learning. So it is very important to understand the logic gate, because in quantum machine learning, when if you want to develop a model from scratch, then you need to understand the quantum machine learning operators, how it is there. Like in classical logic, we like when we develop any kind of hardware system, the computing, the way a computer understand the data. It's not the data we see in the graphical way. Like we see a picture, but internally the picture has a three-dimensional binary data point. So like that, every model in classical machine learning, that converting to binary data, you can see that OR gate, AND gate, NOT gate, and NAND gate also. These are the logical, gate is there always responsible for classical machine learning. If I'm talking about OR gate, what will my input? If I put 0 0, I'll get a 0. If I put a 0 1, I will get 1. If I put 1 0, I will get 1 and 1 1 1. So if I want to develop a ANN model or machine learning model to replica of OR gate, so I need to make a linear separable between the data points. So I need to develop a model that can separate. When I put 0 0, it should give a 0 value. So this is the way when we separate the data points, when we categorically define the like it's a binary classification here. So I if I want to make a separate between 0 and 1 data point, then it's a linear, I need to go for linear. But if you go for non-linear, like a XOR gate, like you need to define a two decision boundary to separate the data points. So this is all about the classical machine learning. And when we try to solve this same problem in a quantum machine learning, then we need to make a quantum circuit. The circuit should behave in that way. So when you have 0 0 input, it should give 0 output. So what is the importance of quantum machine learning at here? Because if you develop a model of replica of XOR gate, definitely your machine learning model should have two decision boundary. Okay, and that should be nonlinear nature. But it takes more computing time, because first of all you need to establish the first decision boundary, then it need to establish the second decision boundary, and then it need to be separate the data points. So that's the computing time. But in quantum machine learning, that is faster, very very faster. That's a speed of kind of things. Okay. See, this is the model structure of a simple network. You can say that it's a two-dimensional neural network architecture. One layer, two layer. One is input layer, one is output layer. The same output, if I want to replica of this OR gate, suppose I need to get 0 0 should be 0. So this is my input. Okay, and I need to define a network which is a summation. That summation should be the interconnection between the input and the semantic weight. The weight is called a semantic weight. It's a replica of your human brain, and you need to multiply the data points with the weight, and with the addition of bias, you need to define the network. So the network output will be the semantic weight with the input. Okay, so if I calculate the neural network output like that, like W1 into input 1 plus W2 into input 2 plus bias. Bias is required to getting the exact output. Then I need to define an activation function. That activation function should convert the value. So there are a lot of activation function is there, hard lim, log sigmoid, tan sigmoid. A lot of activation function is there that converting this value to the next. That is the way we can structure a AND gate like that. So in classical machine learning activity, it is very simple to design because you have a numerical value. You take that numerical value, define the variable, and define the structure. It is very simple, but it is not so simple in quantum machine learning. You need to be define the quantum simulator, the circuit before you define this. This network should be replaced by a quantum processor or quantum circuit. Here I'm talking about this is a network for me, and for quantum machine learning it's a quantum circuit. So there are some of other advanced model structure is there, like deep learning activities, machine learning activity. Like there are a lot of improvement is there in deep learning. There are a lot of convolutional neural network already designed. AlexaNet, GoogleNet, then VGGNet, then LeadNet is there, ResNet, RetinaNet, CapsuleNet. Then generative adaptive network model is there, GAN model is there. So these are the advanced machine learning activities there. Still, all of the activities is based on the numerical values. That's why deep learning, if you want to develop a deep learning model, suppose if you want to develop a object detection model, and you want to use a backend as a ResNet as a backend. So if you imagine like ResNet 152, that means 152 layers are there. So your classical computing is not suitable to handle this type of large computation. And if you want to develop, then you need to develop the parallel computing, a multiprocessing process. You need to adapt to get that computing output. So it takes more time. So then you need to have a GPU for that to training the model. So it's you need to go for a very quality GPU, which is very costly in nature. In a layman kind of things, like if you go with the world advanced GPU, which is Ultra 100 Tesla model, like it's NVIDIA World Tesla V100 model, which is very highly best GPU here. But the cost is of NVIDIA Volta Tesla 100 model GPU is cost of around 18 lakhs to 20 lakhs of rupees in Indian currency. So this is the drawback of deep learning. If you want to develop a model, you need to define, you can develop a model with the cloud support system. Thanks God that cloud is there. But again, cloud, you need to pay per month a subscription charge, which is costful for any kind of model development. So I'm just ending on this machine learning. I hope you got some of background. Quickly, I move to the presentation I made it for quantum machine learning. Tell me, is it visible to all of you or not? Is it visible to all of you?
Yes.
Is it visible to all of you?
Yes, sir.
Okay, great. Okay, so let me start with quantum computing right now. Generally, what happen if you want to develop a quantum machine learning from scratch? There are some concept is required to start with. Like if you want to develop any kind of machine learning model, maybe it is a clustering, maybe it is a regression model, or maybe it's a classification model that need to be some of background it is required. You can develop your model from scratch, but from if you want to develop from scratch, you need to maximum knowledge in quantum mechanics and the process the fundamental processing units of quantum machine learning in detail. That is very difficult to, so that there is last year IBM quantum machine learning team developed a particular Python package. This slowly added other models are there. So it is called as a quantum machine learning package for quantum computing for IBM. So there you can define the you can develop your NN model for that. Today I'll explain how you can develop a model without more mathematical knowledge. Okay. So for that, if you define a quantum computing in nature, it is the fundamental properties of quantum physics. There are three stages are there: superposition, interference, and entanglement. So these are the three major part of quantum computing when you converting your classical data to quantum data. Okay. And basically what is the need of quantum machine learning is it is fully distributed. Okay. And there are a lot of startups are there, like startup I'm not call as startups, it's all are lot of good companies are there that already started the quantum computing, and they already started the cloud service in this way. So Google, Amazon, Microsoft, and IBM has they have the support system for this. But in this comparison, IBM is too good and best in this. So today the presentation today the hands-on I prepare for all of you, it is on IBM quantum computing device. So so this is all about the some small introduction. In future, when you have the data with you, when you converting the classical data to a quantum processing unit, that time the quantum processing unit will be higher capability in terms of in comparison of graphical processing unit. So it is very excellent to use this quantum computing in nature. So I already explained the classical machine learning, how it is behaving. So if you want to develop a classical machine learning activity, and if you want to deploy your model to cloud or in production system, then all of the data is based on the classical data 1 and 0. Okay. And you need a CPU or GPU for processing for that, and you develop a model for this. But in but that takes some time, it takes some computing time. But in quantum machine learning, you need to define the quantum states, you need to convert the classical data to quantum data, which is called as qubit. And then you develop the quantum processing processor, and then whatever the algorithm, mathematical algorithm, which is based on the classical data, that can be converting to the quantum data and quantum processing. So generally what happen, the today's the like if you want to solve so big data in nature, like maybe it is a medical data, like genomic data, like you can like healthcare. Generally one data with in TB kind of thing memory, 5 terabyte, 6 terabyte data, which is very big data to handle. It is very difficult to handle. Right now we are handling the data with using of distributive computing in nature, but it will be easy when we have a scalable quantum machine learning. It's not scalable right now, we are not able to deploy a quantum machine learning model right now. That is, all are the things in R&D stage. See, I already explained all of you that what is a quantum machine learning and what is a quantum computing. Quantum computing is a kind of is a phenomena, is based on the mechanical phenomena, which is superposition, entanglement, and tunneling for the computation. And the quantum machine learning is sometimes if you want to compute or quantum machine learning, it does not meaning that you need to depend upon a quantum computer. But nowadays it's very easy to make a connection between your computer with a quantum computer through CICL mode, which is already available in IBM side. So these are the principles are there. You need to understand what is a key bit in nature. Like when you define your quantum structure, you need to understand that what is a classical bit and what is a quantum bit. Generally, you need to today the Hanson I made for you. It is on key 1 bit operation, but you can go with n-bit operation also, like the classical bit. Like when you define 0 and 1, then you can go with n-bit operation. Like suppose if you're talking about the textual data or a one numerical data, the memory with a numerical data is maybe a kind of a 4-bit or 5-bit nature. But if you move to textual data, then it move to maybe it is 32-bit or 64-bit. But if you move to a image data, which is more value, so like that, your data quality will be changed with respect to the available bit in that image. So you need to understand what is a qubit and what is a classical bit. Generally, when you define a classical bit, one bit means either zero, either one. But in quantum, qubit, it is both zero and one. That is the major difference between the classical bit and quantum bit. At a time, you can define a image with a very small time. Then if you like, why it is more demanding research right now, because if I want to define a image, suppose there will be 10 bit or 20, 16 bit of images there, okay, at a time. So for a classical image processing point of view, I need to define each and each 16 bit, then I can define a image. But in quantum processing, you can reduce that image to 8 bit. Okay, because both 0 and 1, it will be moved with a qubit operation. So it will be reducing that entire image. So the image compression will be very lesser in quantum computing, and in future you will get a result within a fraction of second. So where classical computing takes minutes of time, but in quantum computing it takes less time. This is the major difference between the quantum bit and classical bit. Let Then the next concept is superposition. Superposition means the addition, multiplication, division, and these are the operation. Okay. In classical state is very easy. Either you need to add binary data and then you convert to decimal for display of a data, kind of that. But in quantum computing, the quantum state, it's a spherical nature. So there will be like the distribution is totally uniform in a sphere. So when you define a qubit in 2 to the power n path, so it will be fully distributive in nature. So there will the superposition it will be very distributive compared to your classical superposition, means addition or subtraction or division or multiplication. So when we define a states, generally we need to define 0 and 1 are together. So it is called as ket 0 and ket 1. The right technical terminology is ket 0 and ket 1. Like when you define a 0 kind of position, then it is a one state, and 1 is belonging to other state. So when you combine together, so this is called as superposition. Here you can see that this equation, the psi, with a equation of alpha with an beta. So this is called as a one state, which is have a position of 0 and 1, and that is called as ket 0 and ket 1. Okay. And alpha and beta are the probability of amplitude that representing the state in a spherical domain. So when we define the position of a quantum bit, either we define the north pole or south pole or east pole or west pole. So that will you can define the value of alpha beta in a polar coordinate. So alpha is cos theta by 2, beta is I to power I phi sine theta by 2. So that time it will be converting alpha beta. So when you start the quantum computing as your project, you not to be worried about this value. Actually that already conversion is already there in that library. You need to call the library and that's it. No need to worry about this mathematical operation. But if you want to develop some model from scratch, definitely you need to have understanding of this concept, which is a little bit complex. So you need to understand the quantum mechanics first. So like the qubit state will be the ket 0 plus I into ket 1 by root 2. So when you do for a position for a quantum states, so 1 by root 2 will be there to making that the probability of 0 and ket 0 and ket 1 actually. So then we need to define the entanglement. So similarly, you can go with 2 qubits or 3 qubits in nature. That is called as the entanglement. It is essential if you develop a something model from the scratch actually. Then you need to define the register. So this way you can define like if you want to go with a state a b c d e f g s and in a computational basis, so we can define that that key bit with respect to that state. So suppose if you have a qubit like like what 0 1 0, so it will be 0 0 1 0 0 0 kind of that type of qubit you need to assign in a permutation combination manner with the state actually. So this is called a register. You don't want to be worried about the register, because when you call that quantum circuit, at a time the register also defined. Then if you understand the quantum circuit in nature, then as like as the classical gate NAND or NOT and gate kind of that, then in quantum computer is called as Hadamard gate. So in Hadamard gate, the ket 0 should be representing as a ket 0 minus ket 1 by root 2, and ket 1 will be representing as ket 0 plus ket 1 by root 2. So that is the requirement to define a Hadamard gate. So without Hadamard gate, your quantum circuit cannot be developed. So this is all about the basic knowledge of quantum processor. Then you know, there will be a NOT gate is there in quantum computer. It's called as C naught, and the C naught will be one superposition and one qubit, like ket 1, ket 0, and the plus will be superposition. That's three major part will be defined. So if there will be two qubit, then it will be has matrix of 4 cross 4, 4 matrix. So first one will be corresponding to 0 0. Then second one corresponding second column is corresponding to 0 1, ket 0 ket 1, and third column is corresponding to ket 1 ket 0, and fourth column is corresponding to 1 1. Okay, this way you can define the first column, second column, third column, fourth column, or this way for a 2 qubit. So if your 1 qubit, you don't no need to be defined the C naught gate. But if you have 2 qubit, definitely need to develop a C naught for to configure the quantum circuit actually. So this way you can, like, in future you call me for a brief workshop. I'll explain totally the mathematics. It is it's killing the time. It is very boring kind of thing. So definitely when you develop a quantum circuit, you need to define the Hadamard gate, C naught, and Toffoli gate. And Toffoli gate is required for when you have 3 qubits. More than 2 qubits, you define the Toffoli gate like a C naught gate actually. So these are the defined terminology in quantum processor. Like when you define your C node, when you define your control states, when you define the quantum states, when you define the Toffoli gate, then you need to define the measurement. So for measurement, there is already libraries there, and you can directly call that the measurements, and you define the quantum circuit actually. So is there any question? I can question. I need to take a 1 minute break. So is there any question on this? I can answer.
Yes, sir. Yes, sir.
Okay, great. So slowly I move to the available quantum computing device. There are a lot of advancement is there. D-Wave starts fast, the world fast company who develop quantum computers, but IBM is far away. They develop a lot of improvement in quantum computer. Second rank is there Google. Google is very close to make available in very soon in cloud. Uh, so this is all about the quantum computing devices. Right now, the demonstration today I have for all of you, it is for IBM quantum computing. IBMQ is the execute program for quantum computing. I'll explain how you can register, how you can do your activity in that way. So defining a quantum machine learning, you need to like when you have a defining a function, like when you have a defined function, like here the first image, you can see that you have a x input, and you have no idea what is a function exactly, and you need to predict the y. So this type of operation is it's a black box kind of thing. So when you trend with, like, suppose if you want to predict stock market actions, you have no idea what type of function is. Okay, so you took the data and do the leveling and do the training with the data and to develop a model. And when the model will train with less error, then you deploy the model to the production, and when you have when new data to comes to it, it can predict the sell price or the stock price, like that. So that is called as black box theory. So whatever the machine learning activity that easily handle the black box concept. But when you have a known function, so when you develop an algorithm, you should test your model with a known function. That known function may be a sine function or cosine function. When you have knowing about the idea what is the function is, before you start the modeling, when you have the idea about the data type is exactly, then it's called as function approximation. So today I will give the demonstration for quantum machine learning is on function approximation. So when you have developed a function approximation, you need to develop the you need to like the function. Suppose if you want to make a replica of a sine function, you have x input and y is sine pi x kind of that. Then y is dependent on x and the function is sine x. So the sine x should be replaced by the quantum processing unit, and for that the x input should be replaced by the qubit. And you need to develop, you need to like if you want to develop from scratch, you need to define the entire parameters and the measurement. Then you can mapping from x to your y in a quantum processing, which is very faster. Is called a speed up. And the space and time complexity also very lesser in quantum computing case. With that, let me start with the concept of how we can start with a programming language in QML part. So there are a lot of you know platform is available. One is Bias Fog, which is a Linux machine learning platform. Then is one is QSkit. QSkit is IBM quantum operation. I'm using QSkit for research process because all of the model whatever we are developing right now, we participate in IBM challenges. We already have a position in IBM challenges, and all of the research activity we started with QSkit. And there is a Microsoft Quantum Development Kit, which is very costly, is not free for any student or researcher. So QSkit is free of cost. IBM Quantum right now giving free access to researchers, students. It's not free access to commercial requirement. It is only accessible for the research study, or if you want to make career in quantum machine learning, if you want to do MS in quantum machine learning or quantum computing, then it is for you. Okay. So for that, what will we do? And let me go to this screen. First of all, uh, you need to register your here. You can go with quantumcomputing.ibm.com. You need to go to this site, and you need to register yourself. So when you register yourself, you have a screen like this. Okay, is it visible to all of you?
Yes, sir.
Hello.
Yes, sir.
Yes, sir, it is visible.
Yeah, so you need to go with quantum hyphen computing.ibm.com. You need to go through this website. Like this is a web link for IBM, and you need to register yourself. So when you register, you have account details like this. I created long back actually. So you have uh, see, I got a notification. If you registered like as a company, you cannot get a kind of a link which is not available for commercial purpose right now. It is available for research purpose. So I use it for my research purpose. And here you can launch your, like if you want to make a composer, like if you want to make a circuit, you can use this quantum composer. And if you want to make some kind of Python code like that using quantum computing as a backend, then you can launch the lab. So when you launch the lab, you typically uh, a a Jupyter notebook will be launched. You can see that when you launch that one, you can have the access to use Qskit, and all other version. So this is you can started your coding activity by using this Jupyter notebook, which is available in IBM uh, uh, platform. But you can do with your local system also. But however, your computing speed, memory should be 32 GB minimum. Memory should 32 GB. So if you start with quantum computing or quantum processing as a research point of view, you can start it. But for quantum machine learning, you need this much of requirement. Otherwise, you cannot make computing through your local system. With this, what will the next process? Let me start on that. See, I already told you that these are the programming language environment for QML. I'm using Python. Last 8 years, I'm developing software solution in Python. Before that, I use MATLAB, and Java, and C++ for software making. But after Python, it is very handy, and it is very user friendly, and it is very low cost solution. So most of the 95% people are moving to Python. So for that, you need to make a Jupyter notebook. I hope all of you know about Jupyter, and if not, then you should have a knowledge about on Python programming. Um so I believe that in our course curriculum, Python is included. I have no idea, but if you have knowing about what is a Python, you have a knowledge about Jupyter notebook. Then you can, like in Jupyter notebook, you can develop a model. For a project point of view, you can go with PyCharm. We go with other ID. So here I'm using this Jupyter for model making. So you need to install the Qskit. So you go with pip install Qskit. So when you installing it, you can install your library through directly in Jupyter notebook using this syntax. And when you use it, so this is the way it will be installed. Then you can install
तो यही बोल रहा हूँ कि आपने ये
Qskit machine learning. In Qskit is all about the quantum
sorry to interrupt you,
yeah.
but I want to convey a message to the audience. Uh, Everyone who is having a laptop, they can do this project along with the sir on their laptops. So I recommend everyone to use laptop if they can.
Okay, so for that, let's start with this. Go with quantum computing. I'll share this. Go with this. How we can see this Zoom? Uh, is it visible? This site, https quantum-computing.ibm.com. Go with that slide. Register yourself fast. Without that, you cannot make a machine learning activity. For general quantum computing, you can do it. So open your Jupyter notebook, install pip install Qskit, and remember, who have more than 32 GB of RAM, you can run your model directly. Because when you establish the connection with IBM quantum computing, then you can directly do your coding activity through your local computer also, not a problem. But remember, you can see that I can show you what the issue. The issue is that, as my is a one of laptop, I have other laptop. It's using for other operation. But you see that it is a 8 GB RAM, and up to that, its connection all are made. But when we start the training of the model, it is creating the some issue with runtime error. So that means runtime error comes when memory issue is there. So less than 16 GB, less than 8 GB, sorry, it's less than 32 GB computer laptop cannot be a right choice for this operation. But you can start with this. Okay, install this Qskit. So after this installation is over, you have a typical this type of message, and then you install uh, pip install Qskit machine hyphen learning, this syntax. You can directly install the things in direct Jupyter, or if not, then you can go to the CMD Anaconda. Like here, you can like I already installed Jupyter everything in my system. Who has the already installed? You can do it directly. I believe you already install Anaconda latest version, so you can directly install piv install qskit hyphen machine learning. So
Sir,
you
can
can
you please
directly
show the link once again?
this one.
Yes, sir, for the QML which you have shown previously.
Okay, go with this one. This one. Pip install kyskit
No, sir, the
qskit
link for the
link.
platform.
Oh, okay. Platform. Okay. For platform, you need to go with quantum-computing.ibm.com.
Okay, sir.
Mention your institute NIT Hamirpur. Mention your class. Mention that you are using quantum. Like others, you cannot get a link. Maybe they're not giving for usual activity. You mention that you are using quantum computing for your research operation. There is the option is there. Okay. So after this process, you can able to connect your system with quantum computer for quantum machine learning activity. So is it okay right now? You got it. Like you need to install qskit also in a local system. Either you can go with the Jupyter notebook directly in cloud. It is right now. You see that this is a cloud structure here. All are the code in cloud, IBM cloud, and I can run the code here from here. But here, like here, this code, you can see that it is directly working for my local host, which is my local system. So here it is the you can see that this is the link of this Python file, which is a cloud architecture, cloud platform. But here this one is running from my local system. You can run your code from your local system by connecting your local system with the IBM quantum server. Shall I move to next? You finish this one. So okay, so after you install qskit, then you need to install the qskit machine learning. Simple installation process. Pip install qskit hyphen machine learning. You can install through Jupyter Cell. You can install the this one using your commanding prompt. Then you can also get your version, like you can import qskit, and by calling the qskit version, you can get what is the like I install the latest version. And you see that in qskit quantum machine learning is not there, quantum optimization is not there. If you want to make solution for finance, it's not there. So here, for that you need qskit machine learning. So for machine learning purpose, you need to install that one. So you need to install qskit, uh, this one, and the second qskit machine learning. Okay, after that one, you can see that what will be your computing parameter in your local system. You see that when you like import qskit tools.jupyter, then you can get the version table and the copyright. So when you run this code, you will get a copyright. The code is a part of qskit, uh, 2022 license you have. That means if it is you get an output like this, that means you are get authorized to use IBM cloud. Because when you call qskit, that means you would directly link with your IBM API in that. So you need to have the license for that. So you need to cross check that whether you are getting this information or not. If you are not getting the information, that means your system is not allow to a part of quantum computing. This is very essential. I will share this Jupyter notebook with the team. Then you can go through it and get your knowledge in that. Okay. Any question on this? See, it's my local system, and I have because I'm using Asus computer. It's a i7 computer, and it's a core i9 generation computer, and that is a GPU is there. GPU 1665 Ti is GPU is there, and the RAM, unfortunately, there is two RAM. One RAM is wrongly working, so it's right now 8 GB, showing 8 GB. So which is not good for quantum machine learning, but it's good for quantum computing. Okay. So for quantum machine learning, you need to buy a laptop where you have 32 GB memory support, or you can install extra memory in your system. So up to that, I think your knowledge will be clear on that. So let us start with some kind of more information kind of that, like how you can start with the quantum computing in nature. Like, so you know we all are already here. So see, uh, in literature, the cat 0 will be representing as 1 and 0, like this way. But in Python, you can go with one dimensional, 1 0. Okay, so like that here, you can define your initial state, q state, 0 and 1 or 1 and 0, like that, no issue. But you need to import the quantum circuit from qskit, import quantum circuit. So you need a quantum circuit that when you define qc is quantum circuit 1, that means this variable, which is a quantum operator right now with 1 bit. And what is that initial state? You can initialize with 0 and 1 value. Okay, this, like that. So then you initialize qc, initialize initial state 0. So then it will be complete, like the circuit will be complete. Otherwise you cannot define a circuit. Clear? Shall I move to next? Hmm? Okay. Then you need to have a concept of AER. AER is a high performance protocol. It's defined as AER only. That is, if you have a noise model. Noise model means uh, you need to understand what is a robustness actually. When you develop a system, when you develop a machine learning models, and we need to cross check its robustness. So generally what happen, if your model is not performing well with a high chaotic situation, like suppose there will be high noise, like if you are a human and you are not able to listen someone in a crowdy in a noisy environment, that means your system is not good. Like that, the AER is a library for quantum processor to handle with noisy condition. Like if you develop a quantum processor, and if you call AER as a backend, which is a emulator or simulator, you can take as a circuit. It's a simulator, or it's a emulator kind of thing. So it's a circuit that able to handle the noise. It also, quantum circuit also have that type of ability to handle the noise. For better result, you can use AER for quantum circuit. So what how we can call, like for qskit, import execute. Execute is very important because you need to define the circuit, then you need to execute the circuit. Okay, AER is the circuit, quantum circuit. Okay, which is a simulator. So you need to define your circuit for that. Okay, then you define a variable. Backend is the AER get background, and state vector simulator. Result, you can develop any kind of variable. Result is a variable. Execute qc. QC is here, you define already the circuit with 1 bit qubit. I already update you, like today's hands-on on the 1 bit quantum operator. So you can correlate that presentation here with this. So here I defined the quantum circuit, and I define the simulator, because without a simulator you cannot process the circuit. Who are all are belonging to electrical engineer or electronics engineer, they can have correlated this concept. So you need to you need to define the circuit, and you need to define the simulator first. So after that will be complete, then you can execute the result. So this way you can define the things. Like I can run, you can see that already I got that one. So you can see that is gone. So after you installs and all the things, so you can. So if you want to know what are the simulator, you can also select the, like I select state over simulator here. So I select this one, which is mentioned here. You can also go with other type of simulator here. You can go with QSM simulator, which is the quantum simulator. Generally, for that you need to IBM computing as a link, and Pulse simulator you can use it. So there are a lot of things. So if you run this code AER backend, you can get it this one. Now, I want to explain you the qubit operation. So generally what happen when you do the visualization, how your qubit is assigned, that means the probability should be should be highlighted. Okay. So here you can see that I define a result which is execute a simulator. Here it is the quantum state, and here is the execute. I got the result. So if I want to visualize this result, to see how many counts are there, how many bits are there, because I already told you that there is one single bit I defined. So so like this is important to know about what is I am talking about. Like you need to define the superposition, like in a vector. How you define a vector, like you we define a vector, b vector, then a plus b is like that, the diagonal matrix. So like superposition, when you define that one, when you adding that one, you need to adding in this way, simple matrix addition, and always you have a probability factor with 1 1. So here when you like if you successfully call the quantum processor, your probability should be 1, and it should be the test should be 1. So if I run this, I got a visualization like this. So that means I successfully call the circuit, then I call the simulator, and I make the connection between the simulator and the circuit. Now it is connected, and now it is already defined the one qubit, which is highly probable according to this principle. This principle should be 1 1. So the probability should be 1 here. Okay. Now I define two state. Okay, initial state is 0 1. So I already shown you 0 1. Now I define 1 1. Okay, now it is the next stage. Like it is one stage. Now I define the second stage. Okay, so here what happened when you do the superposition, like here. Now if you add with respect to the positive qubit. Okay, so we need to define the probability value, and that probability value should be a position of 1 by 2. So if you want to make a equal balance between the qubit, one bit operation, then what happen, you need to change your definition. The initial definition is not enough to define way. You can get a error like that. You can get an error like sum of amplitude square does not equal to 1, because it is, of course, it's never 1. Like if you define 0 and 1, and if you define 1 1 1, it cannot be added. If you want and to add it together, superposition together, it should not be 1. So if you run this, if you define this way, you will get the error like this. What is the procedure for this? So you need to define the state like this. You need to add square root here. As per the formula, you can see that if beta is equal to alpha, then your alpha will be 1 by root 2. So to calculate the, if you want to travel with 50-50%, that your ket 0 will be 50% and ket 1 will be 50%, then you need to multiply root 2 1 by root 2 here. Okay, So if you define this way, initial state 1 by square root 2 and 1 by square root 2, and define your circuit, then your result will be like this. And this way you can define the result. You can see that when you add 1 by square root 2 and 1 by square root 2 here, the position changes, like you added alpha and beta. So alpha is 1 by square root 2, and it will be superposition of 1 and 1. Then you have, see that 0 will be 50% and 1 will be 50%. Now your circuit will be defined. So it is a little bit complex, little complex. If you practice more, if you go through the concept, and link with the programming and the theoretical concept, you can get the exact link. Then if you want to make like you see that, okay, let I define geo cat 0 will be 25% and cat 1 will be 75%. Then what will do, according to the principle, you need to define like this. You need to 1 by 2 and root 3 by 2. In this way you can define it. So here, so I say I define alpha will be 1 by 2 and beta will be square 3 by 2, because already I already take one position. So right now, if I run this code this way, you can see that my 0 will be 25% and I will be 75%. So this way, it is you can correlated the operation of the superposition, entanglement, and register this way to analyze the probability factor associated with a quantum processor actually. Okay, so then let's have a problem statement here. I need to close, I need to complete within 10-15 minutes of time. See, so see, this is the problem statement. I think it is visible to all of you.
Yes, sir.
Please tell me, is visible to all of you or not?
Yes, sir. It is visible.
Yeah, see, I want to make a model like this. This is my trigonometrical function. I want to develop a robust model so that it can handle with a chaotic situation. Chaotic situation means noise situation, with noise. Like if I generate a sine function, I add some noise, and now my model should be handle that part. Okay, so for this noisy condition, you know that very few model have that much of capability to handle the noise. MLP also good, multi-layer perceptron, but with noisy condition we need to do some lot of regularization method. Immediately you cannot get exact result. If your noise little bit higher, more than 2 decibel of noise, if you add in the signal, your MLP cannot handle that noise. So you need to go for robust methodology like support vector regression. Support vector regression is very robust mechanism to handle this noise. Okay, so today's like how we like I can give a demonstration on the classical machine learning and the quantum machine learning. Okay, now you can correlate this problem statement with this quantum processor. So this mathematical function should be replaced by this operation. So that Sx and U0 were the quantum pre-processing unit, and the measurement is a part of this. So you need to convert the x to the qubits, and you need to define this Sx and u theta and the measurement. So in quantum machine learning you can directly call this measurement, but if you want to develop your model from scratch, you need to have understanding what is Sx and u0. It is very highly mathematical derivation. I will explain later. If you invite me for a dedicated session for this, I'll definitely explain all the things. So you can correlate this model like this is a right now we need to replace this mathematical equation. So when after training is over, how we do the training, like we have a y, we have a function sin x, and we added noise. We know what is the data is exactly. We have a y, then we need to pass this ML operation, and we get y prediction, we get error, and that error will be minimized by using a updation algorithm. The updation algorithm can be, you can use gradient descent algorithm, you can use go for Adam, you can lot of updation algorithm is there. Least mean square and method is there, RLS method is there. So we can adopt any kind of updation method so to minimize this error. So here in updation, the optimization function, objective function, you need to take it the error function to be objective function. And after some training will be over, when you minimize this error, so your ML will be behave like as a sin x with noise condition. With noise, with chaotic situation, ML can understand, oh, this function is sine function. Okay. So when you have new input to this, as already the model trained with noise, so whatever the, like if you add some noise here, suppose in real time, when you do develop some application real time in industry purpose, like sometimes when you work with the sensor, so sometimes due to temperature issue or due to some kind of error, so noise will be added in directly in the sensor input, so you get a noisy signal. So that time, if think that there is a noise is added in input signal, no need to worry about, because your ML is already trained with a noisy signal. So when a new input comes to ML, you get the exact sine function. So for this, I need to show you the classical coding, then I'll show you the quantum processing coding. Okay. With this, let me define this way. So see, and it's not required. So you need to install all of the your Python package. You see that I use a Python package of 3.7. It is installed last year. So right now it is 3.8 is already is there. In IBM Cloud it is 3.8, I think. Let me cross check exactly if you see the version. Yeah, it is there, 3.8.12 in IBM Cloud. So see, this way, you see that I defined a NumPy. NumPy is responsible for all of the arithmetic operations, and I directly use a library here. For support vector machine, I use sklearn, scikit-learn kind of library. From scikit-learn neural network, you can use ML regression. So this is a regression problem. So I develop a the data point. Here you can see that I generate with a random variable between 1 to 200 data points are there, and I generate this is the output, original output, with signal, with sine signal. Okay, original output. And then I added noise. So here I added up to zero point 0.3 decibel of noise. Actually, if you convert this value to logarithmic value, 10 log base 10, you can get a noise. So I added noise with y. So right now you got it, like this data point, you can see these are the data, so it is noise, but the data, exactly the data is a sine function. Okay, we need to make it to function affirmation on that. So I defined a RVF function, which is a SV, support vector machine, and I define multi-layer perceptron regression. I need to define all of the parameter. I need to define the momentum parameter 0.001. Hidden layer, I define like two. There is four layers. First one is input layer, second one is the two hidden layer, and last one is the output layer. So this way I define the hidden layer size. Iteration, I took it more because here, as it is it cannot handle zero point 0.3 decibel of noise, and we need to do a lot of regulation factor to get correct output. But if I run this code, you can see this is the output where support vector machine with RVF kernel is fantastic to handle the noise, but here MLP is not. So these are the issues happen in classical machine learning. So we need to make it to a lot of regulation method like that. So to avoid these things, you can see this problem. It can easily handle with quantum machine learning. So for that, if you want to work on quantum machine learning, there are a lot of background knowledge you need to know about tensor. We need to work with storage. We need to have background knowledge about object detection algorithm. You need to background knowledge of deep learning. So then you can have a correlated with this type of activity, or else it's a little bit complex for all of you. So I use a torch. Torch is a Python library which is very very high powerful tool where we develop object detection algorithms. We deploy models with respect to torch. So I already developed a lot of model I deployed in torch and also in TensorFlow and keras. And but it's good. Torch is good. It's very lightweighted. All of the models are there. You can directly call the backend structure directly. You can directly call FRCNN. You can directly call MRCNN models. You can directly call RCNN models. So retina rate is already available in the library. So this is all about the torch actually. So I need a tensor. What is a tensor actually? We need to understand what is tensor before we proceed to quantum machine learning. See, if I define a scalar, a numerical value 1, if I move to vector, I need to define what I need to define. I need to define the direction and define the direction of a and direction the vector direction with a projection angle. So here, so for this, if I make a vector, I need to define a boundary, and I define I if I um, make the scalar be available in this dimension is a vector which has no like is a angle of 0 degree angle kind of that. So if I extend the dimension with other with numerical value, it's called as matrix. But if I, in a matrix, in multiple matrix, if I define another dimension which is called a tensor. So tensor is a kind of like with multiple matrix with respect to a multiple direction. So it's a three-dimensional matrix. So you can convert the matrix to tensor. So if you have a scalar input, if you have x input, like in that classical machine learning part, you can see that when I define the data point, which is a scalar, then I need to convert the scalar to array to matrix to tensor. So which is very difficult in that. So for that, I need to use Troch. Directly, I import tensor, manual seed is for multiprocessing tags, and tensor. Then I need to import linear cost and entropy loss, like when you cross-checking your model performances, you need to define the cost and entropy loss. Cost and entropy loss you already know about in cart model, decision tree model. When you define lot of branches, multiprocessing, all are losses. If you add together, it's called as cost and entropy loss. Cost and entropy loss is very important to know in object detection models. When you have lot of data points, you need to know which layer is getting the loss. So that's cost and entropy loss. Again, I need to define the mean square error loss. Similarly, I need to do the optimization. Adam is a powerful updation. Like here, I already explained you that the updation algorithm here. So here the updation Adam. Even in MLP, you can also define that optimizer. So similarly, I need to define the qskit. AER I define, quantum circuit I need to define. Then all are the like related terminology, like it will I need to define the instances, I need to define the algorithm globals. Okay, then it is very important to define the parameter is essential to define the structure, actually the quantum circuit structure. Okay, then I need to define the future map is very important. Like when we converting the numerical value to key bit operation, the future map is very important. So here I need to call the quantum machine learning neural network. So you see that when I call two-layer QNN, that is two-layer quantum neural network. So you don't need to go with the concept of superposition, entanglement, register, Hadamard. No need to go with that. I no need to worried about the measurement that is already defined in this structure. If it is two-layer neural network, two-layer neural network means uh, uh, like this already defined. Like here, one input layer, one hidden layer, one output layer. That's a simple structure. Generally, there are a lot of things are in processing stage, so you can directly call the two-layer QNN here. Then you need to like connector between the torch parameter. Like torch is a platform where you can train your model. In quantum machine learning, you can define the quantum structure in terms of you need to convert your theory, your mathematical equation to a quantum related equation. Okay, then that connection, you define the circuit, and you define the model that need to be connected. So you need a torch connected here, and definitely need a client, torch, torch runtime client, and time result for to getting the all of the result of the model. See, this way you can define. Then I define the similarly. I need to define the data. I need to define the lower limit minus pi to pi, and I define the sample in that way. And I define the function already. It's a sine function. You can see that f is a sine function. Then I add the noise. So this is the noise part. Okay, that's same noise I added here. It's a little less noise, but you can go with zero point 0.3 or kind of, so it's a zero point 0.2 noise. Okay, zero point 0.2 decibel kind of. So if I add it, then I need to run this one. See, this is the kind of representation of the sine function. Then I need to scaling to into data point. Like I need to make it to tensor. So you see that I define the x value, I define the y value. I need to make it to when we defining machine learning, we need to define the parameter as a numerical value of float parameter kind of that. Similarly, I need to make it to tensor. So this is this function I written to converting the x and y to the tensor. So it returning the tensor value. So I need to go with a training data set, and also I need to load it to a data loader. It is very important because it need to be an object kind of thing. So data loader I already call, like you can see that database and data loader. So it will be a kind of a inject of you can say that is it's a package kind of data. So I cannot travel with one data point. I need to define all the data point together. So after that you can split your data 50%, 80%, 20% like that. But here in this problem I'm not splitting it. Whatever the data point of x, the training data point is the testing data point. Okay, now I need to define the quantum circuit here. So I need to define the parameter. So for, like, we have two parameter. One is input parameter x and y. That's why I called two dimensional two dimensional quantum neural network. So here one input and one output. That is that if you move to a complex architecture, you need to convert, you need to develop your model from scratch. Or right now there is no multiple QNN is there, they're developing, it's in developing stage. Very soon it will be available in literature, and I think that you can use it. But you can develop a two-dimensional neural network architecture here. So you define the parameter here, then you define the circuit. I already explained you how you define the circuit in that previous uh, then you define the converting that features here. So again, with this, with the help of parameter, you converting numerical data, the tensor data, to a qubit data. Okay, then you define the QNN. So you can call two layer. Okay, one is the state of the the you can see that the state is one. That means one qubit machine learning approach, and define like the future map is the quantum circuit, and you define like the x input. Okay, then you define the initial weight, like similarly the when we initializing the weight and bias, this way we define the weight. So accordingly, like if you if it is x, the number of weight is depend upon the number of hidden units in the hidden layer. So that I need to define it, and then I make a model. This model I need to connect it the initial weight and the qnet here. So this model for connecting, I need to use torch at here. So here your quantum circuit, which is right now converting your classical bit to your quantum bit, and then the initialize the weight, and then you make the model. Now it is connected with the platform of torch. Now you can do the training. So for that you need to define the updation, the optimizer for that. Okay, so for that you need to define the Adam is very popular optimizer we are using most of in quantum sorry most of in object detection and deep learning models we are using Adam. And for to do the loss function, I use mean square error loss. But this is a simple problem. I use mean square error loss. So when you run this, see, this is the structure. If you get a structure like this, then it will showing that how it is connected. So this is the object. This is the quantum circuit object, and this is a kind of a layer for quantum computing. Okay, so up to that, your operation is over. Now you need to connect with the quantum computer. Here you can see that this is a platform of quantum computer. So you need to go with registration. You need to do the tokenization. You get an API token. Again, you can regenerate the token. So token is kind of like, if you go with account details, here also you generate the token, API token. So API token means the linking between your system to the IBM system. As it is already in IBM system, so may not you required your the API key. You can directly connect, but I for a betterment, you generate the API key and provide here. So for easy kind of if you want to start with your local system, here I see that I want to see this way I connected my local system to the to this IBM computer. So through this same API key, same token I used. And the simulator is already QSM simulator, which is very best for quantum computing. You can see that I already explained what are the simulators are there. You can see that it is there here. You can see the this simulator is required for quantum processing kind of this. So you need to use it for quantum machine learning for good result. See, then okay. It's showing that already user session. Okay, it's I need to delete the account. Then I need to use it. Okay, one second. Oh, I use that code like that. I need to delete the account here first. Sometimes you it happen. You need to delete the account. Then you need to again need to re-establish. I think it will be okay. Okay, already using an IBM. Okay, here I think it's a problem. I think I need to delete that account. At a time I call here. What's happening? Okay.
Sorry to interrupt you, sir. Since we are running out of the time and lots of questions are
Yeah.
coming, so to proceed to
Okay.
Q&A
So
session,
quickly, I just want, like, it's a error is coming. I need to see what happened, because there's already a working some due to, like, it is I call that the link here in local system, and then so that's why it's have a issue. But you can see that you can make a beautiful robust application, where you can see that the model is approximate the function very well. And if you see the execution time is 0.4 second, the enter things, and you can see that training which is takes 14 seconds, which is very faster. Yeah, I'm ready for any kind of question.
uh, so
So,
Yeah,
yes, sir.
it's a very lengthy session, that
Okay, sir.
uh, yeah, sure.
Thank you so much, sir, for
Hmm.
enlightening us with this wonderful talk. Surely some of our viewers may have some questions about the same. So we would like to get started with the Q&A session right away.
Yes, sure,
You
very
can
sure.
ask your
Thank
questions in the comment section.
Sir, I have one question from my side that
Hmm.
can AI even work beyond human intelligence imagination? Sorry.
Okay. Is there any question from like I can't get it your question. Can you repeat again?
Yes, sir, sure. Sir, my question is can AI ever work beyond human imagination?
I have a call. I need to receive it. Spurs, I think we can go for a next session. We can discuss. I have a call. Very important. Give me 1 minute. Give me 1 minute.
Okay, sir.
Sorry, I've got a call from a client. In the time. Yeah. Yeah, but Vansika, you asked some question. We are in industry and get some call. I need to. Okay.
Yes, sir. No worries, sir. No worries.
Okay.
Yes, sir.
Yeah, Vanshika, you can
What's the
ask your
question?
question.
What's the question?
Sir, am I
What are
audible?
the application of quantum computing? It's a big application, dear. It's the era of AI starts right now, and in the future, can you already watch science fiction movies, right? Futuristic to what will be our life in 2050, 70, the prediction. So you see that the way we are improving our day-to-day life, we have lot of data, we have high volume of data we will receive from next to future, like we have 5G with us very soon. It's not fully operated in India, but it is already operated in other countries. So you cannot imagine like when you upgrade 5G to 6G, 7G, 8G. So that time for kind of any kind of application, then quantum computing is required. Lot of application. Weather forecasting will be within 1 second. You can do the navigation within a five minute or 1 minute, kind of like what will the biggest problem of world right now? Climate modeling. That is the biggest problem of world. It takes supercomputer to compute climate modeling. Okay. And climate modeling, if you if you use quantum computing, it will be in less hours. Right now, for climate modeling, you can search in Google what is climate modeling is really. People are using supercomputer. It takes 1 day for a supercomputer, but in quantum computing it will be lesser, faster.
Okay.
Yeah.
So there is one more question from the audience side. Is quantum machine learning better than the normal machine learning?
Yeah, of course.
Sir, how?
In terms of the robustness, I already told you like what is the robustness meaning. Like suppose you are in a classroom and you want to communicate with your friend, and all of your friends are talking each other. So how will communicate it with your friend? You can call your friend to come to closer to me so that I can communicate with you. Suppose your friend will be right now extreme corner and all people are talking each other, and you are able to communicate with your friend. That means your system, your ear, the microphone, the receiver is so good, so that you can communicate. So that is the way you can design a robust system.
Sir, there is one more question that what do
Next
you
five
think is the
years,
future or scope of quantum machine learning in the next 5 years?
Yeah, it is right now in developing stage. I already told you like there are lot of things need to be developed. Um, you can participate in the IBM competition. You can go through, register yourself, and you start your programming skill, improve your knowledge in machine learning, and definitely many companies have started that activities. And if I am getting benefit, then definitely you're getting benefit.
Sir, there is one more question from the audience side. Where can we learn the new concept related to the quantum machine, quantum computing?
First of all, you need to, like I'm giving one example. You are saying that you are from chemical background. What is the background of Sundar Pichai? It's a metallurgy background, right?
Yes,
I
sir,
done the GI.
methodology.
Yeah.
80.
So
Yeah.
yeah, he has no typical IT background like us electronics and computer science students. So remember one thing: you need to define your logic. You need to strong in computing. You need to strong in coding. And when you making that type of things, you can start a career in that. And right now, it's a very emerging field. You can start your career. You can like if you want to develop a project in that, you can negotiate your with company in your campus placement. You can say that I developed this project with quantum machine learning or highly integrated, machine learning, robust system and design. Then, of course, you have a yeah, excellent. But the roadmap should be like that. You need to understand your coding capability, coding skill. Okay.
Okay. I think so. That's all from the audience side, sir. So
Okay. Great. Great. Thank you all. Thank you, sports, for your invitation. I know it's around 7:40. We are
yes,
habituated to work for 9 hours, 10 hours. So, but a
yes.
student, you are exhausted. So, how is your workshop is going? As good. My best wishes is always with you, sports, and thanks all of the team of NIT Hamirpur. Definitely, if uh, you know, I've really enjoyed
Yes.
the session. I think it's good. Thank you
Thank
very
you so
much.
much, sir, for taking
Thank
the
you.
time to share your thoughts on such an important topic with us. This
Thank
session
you.
will undoubtedly stay with us for the rest of our professional lives.
Yeah, in future, if you design a particular code, like a lot of things, it cannot be complete within a 2 hours, 3 hours. It should be designed in a weekly program, and we can have a better, concept in that. Thank you all. Thank you all. Good day.